Hello everybody, this is Dr. Christopher White and today we're moving on to lecture number 14. So as part of lecture 14 it's split into two parts. So the first part is going to deal with the early Paleozoic, and the second part is going to deal with the late Paleozoic. So we're going to be looking at the evolution of the continents with a special focus on what's happening with North America. So we're going to start with the early Paleozoic, and that's going to be the Cambrian, Ordovician and Silurian. So by this point we've made our way all through the Precambrian, and we've formed a substantial portion of most of the continents, and the first three supercontinents have also formed. So we've had Nuna, Rodinia and Panatia. So Panatia existed between 650 and 550 million years ago. And it's the breakup of Panatia that helps to, as one of the reasons that we can mark this transition between the Proterozoic and the Paleozoic, so between the Proterozoic and the Cambrian. So the breakup of Panatia and a sudden rapid increase in flora and fauna marks this transition. So during the early Paleozoic, sediments will be deposited on the cratons, producing platforms. So of course those are areas where we have Precambrian crust that's covered over by younger sediments, and shields, those are areas where we have Precambrian crust that is exposed. So remember that. So we have platforms, that's where the Precambrian crust is covered up, and shields where the Precambrian crust is exposed, and of course those two combined is referred to as the craton. So the rocks deposited onto the craton during the Paleozoic consist of a mixture of detrital and chemical sediments deposited in shallow seas underlain by continental crust. So what we're going to see as we move through the Paleozoic is we're going to see on 4 occasions a significant portion of North America is going to find itself underwater. The sea level is going to rise and the continental crust is going to be inundated. And this process of inundating the continental crust is going to produce lots of shallow seas. And these shallow seas are called Epeiric seas. During the Paleozoic and the Mesozoic, these Epeiric seas will transgress and regress during periods of continental glaciation and or plate tectonic movements. There's a couple of reasons as to why the sea level is going to go up and down during the Paleozoic, and that's obviously going to have a serious implication for, whether the ocean is kind of moving onto the land or whether it's retreating back into the ocean basins. So sediments within these seas would have been, of course, deposited as horizontal layers. However, tectonic pressure could lead to the formation of gentle regional folding, producing features like arches, domes, and basins. So, bear in mind, it would have been nice horizontal sheets, but of course, during that time, there would have been tectonic forces going on that would have caused these nice horizontal layers to warp. So in many cases, the topographic highs created will form little island chains, and these would be eroded, and that would supply sediment into the surrounding Epeiric seas. So are there modern Epeiric seas? Well, the answer is yes. So if we look at a few examples, we have the Hudson Bay up here. So shallow water underlain by continental crust. We have the North Sea in Europe. We have the Baltic Sea. We have the Gulf of Thailand, we have the Java Sea down here, and we have the Epeiric Sea here between Australia and Papua New Guinea. And so you can see that these areas of continental crust that are inundated still exist even now. Now, another thing that we need to remember is the term mobile belt. So mobile belts form during continental convergence when marine sediments are deformed and intruded, producing mountains. So if we look at this map here of North America, what do we see? Well, we can see essentially we have 4 distinct mobile belts that are picked out by this particular diagram. So we have the Appalachian mobile belt running down the eastern seaboard. We have the Cheatham mobile belt down here covering portions of Texas, Oklahoma and Arkansas. We have the Cordilleran mobile belt running up the western seaboard. And up here we have the Franklin mobile belt, also called the Inuitian mobile belt, which is occurring up here along the northern margin of North America. And so these are areas where continent-continent collisions or collisions between continents and island arcs have produced essentially mountain ranges. And the reason they're referred to as mobile belts is, of course, the belts themselves, they shift. mountain range isn't actually stationary, depending on where the impact's occurring and how forceful the impact is, or whether the impact is waning. Essentially, that will control how the mountain belt essentially is, the morphology of the mountain belt. And so the mountain belt itself will shift and will move around to some degree. So we need to bear this in mind. So not only do we have, during this time period, we have the deposition of lots of nice horizontally bedded sediments into shallow seas covering large portions of North America, we also have the formation of several large mobile belts along the eastern, southern, western and northern margins of the continent during this time period. So it's all going on. So what's happening in terms of paleogeography? So as previously discussed, if you work out the depositional environments for rocks of the same age from numerous locations, you can produce a paleogeographic map for a region, a continent, or even the entire world given time and sufficient data. So as oceanic crust from this period has been destroyed and magnetic signatures in rocks have had more time to be reset, the exact distribution of Paleozoic continents isn't too clear. So when I show you the diagrams and the Paleozoic continents moving around, we have some idea where they are, but we can't be 100% accurate. So we need to remember that the oldest oceanic crust we have dates to the Mesozoic. So that means any oceanic crust before the Mesozoic, that's gone. And so that would have been really helpful to have had, because that would have told us which way the spreading margins were pushing the continents. But unfortunately, it's gone. There's nothing we can do about it. So what do? Well, we look for structural relationships. So we find areas of rock that have been deformed. So for instance, if we go back to this diagram here, when we think about the Appalachian mobile belt, we notice that the way the rocks have been deformed here is very, very similar to the way that the rocks have been deformed in northwestern Africa. And that deformation occurred at the same time. So the deformation we see in northwestern Africa and the deformation we see here along the eastern seaboard occurs at pretty much the same time. That's a strong indicator that those two pieces of continental crust hit each other. And so we can use that kind of relationship to show that, right, well, clearly if they're hitting each other, they have to be in close proximity to each other. What else can we do? Well, we can look at climate-sensitive sediments. So there are certain types of sediments which we've discussed in the past that can only form under a very strict range of conditions. So red beds. We've discussed how red beds, these red clastic sedimentary rocks, tend to be associated strongly with arid to semi-arid conditions. Evaporites, well, evaporites obviously can only be produced where you have bodies of water evaporating away. Once again, where you have layers of evaporites, that tends to suggest you are in dry or arid to semi-arid conditions. So that tells you about somewhere where you are on the surface of the Earth. So there are only certain regions of the Earth where, based on circulation of the atmosphere, that will tend to be drier, and therefore more likely to have deserts in them. And so you can say, right, chances are the continents were in one of these regions. Then there's, some sediments like coals. Well, coal only will tend to form in swampy environments that have a very, very high amount of organic material. Well, that tends to occur in equatorial regions. So typically regions, 30 degrees north or south of the equator. So as soon as you find a coal layer and you can date that coal layer, you can say, right, at this point in Earth history, the continent was probably somewhere in one of these regions. And of course, there are carbonates. Carbonates tend to occur in, once again, very relatively warm shallow seas located typically 30 degrees north or south of the equator. So once again, when we start finding carbonates in our rock record, that suggests that in all likelihood at that period of time the continent was located somewhere near the equator. And now, of course, we also have fossils. And some fossils will have very distinct environments in which they like to live. So of course it's going to give you some information. So for instance, a dinosaur, dinosaurs did not live in water. So if you find dinosaur fossils in your sediment, you have to be looking at a continental sediment. Then there are certain organisms like foraminifera that can only exist in, certain species of foraminifera that will only exist in certain water temperatures, certain water salinities, so that will also help us to gauge where we are on the surface of the Earth. So there's lots of information that we can work with. We can also use paleomagnetism to work out where continental rocks form. That'll also help us a little bit. So, using all this information and lumping it together, we can work out with a relative degree of certainty where the continents were on the face of the planet at any given time. So, during the Paleozoic, we know there were 6 major continents. Baltica, so that's Western Russia and Northern Europe. China, that covers an area that includes China and mainland South and mainland Southeast Asia. Gondwana, so that's a continent that contains Africa, Antarctica, Australia, India, Madagascar, parts of the Middle East, parts of Southern Europe, and Florida. We have Kazakhstania, that contains portions of Central Asia. We have Laurentia, that's North America, Greenland, Ireland, and Scotland. And we have Siberia, that's Russia, east of the Urals, bits of northern Kazakhstan, and Mongolia. So you can see there are pretty substantial pieces of crust moving around. There were also several microcontinents that were moving around. Now, these microcontinents will have come and gone depending on whether they're crashing into the larger continents or not. And on the whole, we're not really going to worry about them too much. The one we are going to be concerned about, though, is a little microcontinent called Avalonia, and that includes portions of Western Europe, Newfoundland, and New England. And that's going to be important because it's going to help explain some of the stuff that happens along the eastern seaboard of the United States. So we won't worry about the microcontinents too much, as I said, and island chains too much, because we're really focused on the bigger picture on the whole. Okay, so what's happening? So during the Cambrian, the continents were located at low tropical latitudes, the poles were ice-free, and the oceans circulated freely. So let's have a look at what's going on. So here's Laurentia. So that's North America. So that's Laurentia, which of course consists of North America, Greenland, Ireland, and Scotland. So this is where we are. Okay, and at that point, North America, Laurentia, is situated on the equator. So we can see we have a few important things going on. So here's Avalonia down here. Here's Baltica over here. On the other side, so there's Siberia there. We have Kazakhstan here, China, and here we have Gondwana. Okay, and you can see this is a very, very large piece of continental crust here. And we can see that it's located essentially in a very high southern latitudes. So you'll notice no ice at either pole. That tends to suggest the global climate was on the whole quite warm. And that will have been helped by the fact that the oceans can circulate freely. So warm water from the equator can move very, very easily towards either pole, and that will help to keep the temperatures towards the poles much, much warmer than they would be compared to the modern environment, where we have lots of continents spread out over the entire surface of the globe that tend to get in the way of ocean circulation and keep the temperatures towards the poles colder. So by the early Ordovician, what's going on there? So by the early Ordovician, we have Baltica and Siberia have kind of drifted northwestwards. So they're starting off down here, and they're heading in a kind of northwesterly direction. So they're heading this way. Baltica's going to come up this way towards the equator. So here we go. So there's Baltica there. So that's moving in a northerly direction. So Baltica's coming up this way. Avalonia is moving around here like this and is coming up towards Baltica as well. And Laurentia is staying pretty much where it is. It's sitting at or slightly south of the equator. That's staying on the whole mostly stationary. In terms of Gondwana, we begin to see Gondwana moving down towards the South Pole. And what we begin to see is as Gondwana moves down towards the South Pole, we replace sea. Now, the nice thing about seawater is it's very, very good at retaining heat. So the oceans are far more efficient at retaining solar radiation than the land is. So, during the Cambrian, we had shallow oceans down across the southern poles here, and so that will help to keep this area here warm. As you move into the Ordovician, we can see the continental crust starts to drift down. That means less solar radiation is being retained over the southern pole, and so that encourages the formation of ice sheets. So we begin to see glaciers forming essentially on Gondwana during the Ordovician. So we see the formation of glacial tills starting. So by the late Ordovician, we see that Avalonia has collided or is just about to collide with Baltica, forming one landmass. And we can also see that this body of water here between Laurentia and Baltica is being destroyed. So the oceanic crust here is being subducted below Baltica and Laurentia, and it's being subducted away, being destroyed, and Baltica is moving towards Laurentia, and Laurentia is obviously moving towards Baltica, and there is going to be a big collision. And this collision is going to produce a couple of mountain ranges. The Caledonian mountain range is over here on the Baltic side, and we have the Tectonic highlands over here on the Laurentian side. Okay, and they're both being produced by this impending collision. By the Silurian, what's going on? Well, Siberia's kept moving north. Gondwana is still moving south. Now we can see we've actually lost the ice cover here. So that would rather imply that global temperatures have increased again, making ice cover on the South Pole difficult to achieve. And we can see by this point the Iapetus Ocean here between Laurentia and Baltica, well, that's pretty much gone now. We can see Baltica has made contact with Avalonia, and Baltica has made contact with Laurentia, and we have a continent-continent collision going on. And obviously that's producing the Caledonian Mountains and the Tectonic Highlands. So that's a general overview of what's going on in terms of the position of the continents and the large collisions that's going on, especially with reference to Laurentia, modern-day North America. So, early Paleozoic Laurentia. So the Phanerozoic sedimentary record for North America contains 6 Cratonic sequences. So a Cratonic sequence is a large lithostratigraphic unit representing a major transgressive regressive cycle bounded by craton-wide unconformities at the top and the bottom. So essentially, it's a sequence of rocks that essentially shows a transgression going on, a very large marine transgression, followed by a very large marine regression. And at the top of that sequence of rocks, we have an unconformity, and at the bottom of that sequence of rocks, we have an unconformity. And as part of the rock record of North America, we have 6 of them. So the transgressive portion is often quite well preserved, because obviously as the oceans transgress onto the land, well, that's protected by new sediments being deposited on top of that transgressive sequence. Now, the regressive sequence, on the other hand, that's often partially or in some places totally missing, because obviously that portion gets exposed to the atmosphere as the sea regresses, and of course when it's exposed to the atmosphere it will undergo erosion, and so in some cases it can be completely removed. So where rocks of similar ages are preserved, the 6 unconformities are observed to extend across or over very, very large portions of North America. So some of these unconformities that we see are actually global. So we see the same thing, we see these unconformities with these large areas of continental crust being exposed at the same time globally. So these changes are of course due to sea level changes due to tectonism or glaciation. They will obviously have a global implication. So, you know, if there's large scale glaciation going on, that's going to lock up water. That means sea levels are going to drop. So you're going to see a marine regression, not only in North America, but also in other continents as well. So when we look at this diagram here, what do we actually have? So this diagram here shows you in brown periods of erosion and in white periods of deposition, and where the deposition is taking place. So this side of the diagram represents the east coast of the United States. This side of the diagram represents the west coast of the United States. So at the start of the Cenozoic, nearly all of Laurentia is exposed, so it's above sea level. So we have erosion going from the west coast all the way over to the east coast. There's near complete erosion across the entire continent. And so this means we're going to have a continent-wide unconformity forming. So what we see as we go through the Cambrian, we see the sea begins to come in, it begins to transgress from the west, and it begins to transgress from the east, until approximately the Cambrian Ordovician boundary, when a large portion of North America is underwater. So we have essentially a body of water that covers nearly all of North America. So we have a body of water, so you could sail essentially from the east coast all the way over to the west coast. Now that body of water then begins to regress, and we begin to see more and more of the continent becoming exposed, both on the west coast and the east coast. Then, during the Ordovician into the early Silurian, we have another marine transgression. We see the sea starting to transgress in towards the centre again, once again forming a continuous ocean going from the east coast to the west coast. Then, as we move into the mid-Silurian, we see a marine regression taking place, so the sea moves back towards the coast. Then there's another marine transgression, regression, big marine transgression, marine regression, another big marine transgression, and then we have a marine regression, transgression, regression. So those are the cycles, and this diagram kind of shows you what's going on. And you can see there are 6 of them: the Sauk, Tippecanoe, Kaskaskia, Absaroka, Zuni, and Tejas. And we can also see marked in this diagram, we have the major orogenies, the major mountain building events that take place. And they're split into those that occur on the east coast and southern portions of Laurentia, and those that occur along what is now the modern day west coast of Laurentia. And so on the east coast we have the Tectonic, the Akkadian, the Achetan, and the Elegahenian. And on the west coast we have the Antler, Nevadian, Sevier, Laramide, and then at the top here we have the coastal ranges, but we're not really going to discuss those too much. Okay, so the identification of Cratonic sequences will be left until we've had a break. So, alright, this is a good moment. Let's pause the presentation, get up, have a walk around, go and get a glass of water, and please come back in a few minutes. So these Cratonic sequences, as I said, are bounded by large unconformities at the... Okay, that's me not turning off my iPad. There we go, serves me right, I apologise for that. Anyway, where were we? So the identification of Cratonic sequences is based on your ability to spot the large unconformities that occur at the upper and lower margins of the sequence. So these unconformities allow us to correlate essentially across the continent. So if we go back to the previous diagram here, you can see based on the unconformity that's forming here during the period of erosion, we can correlate rocks on the east coast to rocks on the west coast relatively efficiently. So this allows for very, very high resolution analysis in terms of rocks, and of course in geology, rocks represent time. And it also allows us to do facies analysis of the relationships by using the sedimentary rocks. So we can see essentially as we come across the continent, we'll see changes in facies, and we can date these changes in facies based on what's going on in terms of the stratigraphic sequence. So we use these packages of rocks to do what we refer to as sequence stratigraphy. And it's the study of rock relationships in a time stratigraphic framework of related facies bounded by erosional and non-depositional surfaces. So essentially within these within the rock record we have these 6 sequences, the ones we spoke about, the Sauk, Tippecanoe, Kaskaskia, Absaroka, Zuni, and Tejas. And within them there are obviously going to be smaller cycles which will also have erosional boundaries at the top and the bottom, and we'll use those as well. And we use these units, these formations, essentially to allow us to do sequence stratigraphy that can, in some cases can allow us to tie up rocks, on the east coast to rocks on the west coast. And of course we need to always bear in mind unconformities represent periods of when we have decreases in sea level leading to the exposure of continental rocks and the process of erosion, which obviously creates the unconformity because erosion causes us to lose rock and therefore we lose time. Alright, so let's start with the Sauk sequence. So that makes its appearance in the Middle Cambrian and it goes through to the early Ordovician. So it represents the first major transgression onto Laurentia. So in the early Cambrian, Laurentia was sitting approximately on the equator, where it was being rapidly weathered, with the resulting sediment being deposited along the eastern and western passive margins. So we had huge rivers cutting across the continent, dumping sediment on the east and western coasts. So in the Middle Cambrian, we see the encroachment of an Epiric Sea from the east, south and west. We have a very large marine transgression going on. So by the late Cambrian, only a portion of the Canadian Shield and a chain of large islands called the Transcontinental Arch, which extended from New Mexico to Minnesota, were above sea level. So the sediments of the Sauk sequence were deposited in shallow water, and we see the sandstones are clean and well sorted, contain ripple marks and small crossbeds. So that would suggest that they're being deposited into a shallow sea where the sandy sediment's being churned up by typically wave action. We also see there are lots of carbonates forming, and they contain stromatolites and ooids. Once again, a very, very strong indicator that you're dealing with a very shallow water environment, because stromatolites need shallow water to exist. The water depth can't be too deep. Same with ooids. In order to form ooids, you need to have the water being constantly churned up by the action of waves. So you can't have ooids in deep water. So this diagram here kind of gives you an idea of what we're basically looking at. So you can kind of just about see the outline of North America here in blue. And this is obviously Laurentia here. And you can see the portion along the margin of Laurentia, well, that's referred to as the sandy bottom. And that's because this area here is a shallow epiric sea where we have lots and lots of detrital sediment being deposited by these very, very large rivers. So we have lots of sandy sediment in this area. So that's where we're getting these sandstones. They're clean, well sorted, and they contain lots of ripple marks and small crossbeds. Now then, as we head out into slightly deeper water, the water becomes clearer. It's still shallow. It's warm because we're at the equator, but it has very little detrital sediment suspended in it. So we have nice clear water, and so this is where we get carbonates forming. So we get large-scale limestone formation in this region, coming all the way around here. And then as we go out, we head out into deeper water, and then we head out into the muddy bottom. That's where we're getting these deeper marine sediments forming. So the deep marine sediments obviously tend to be quite fine-grained and dominated by silt and clay. So by the late Proterozoic, this diagram here kind of shows you, so this is the late Proterozoic here, we have Laurentia fully exposed, producing a continental-wide erosion, which leads to a continent-wide unconformity. So we have essentially what would be considered the modern-day west coast of Laurentia, and here's the east coast, and you can see it's exposed from all the way from the west coast all the way over to the east coast. You could have walked from one side to the other relatively easily. Now, in the early Cambrian, as I said, we begin to see the seas begin to make their move. So the seas begin to transgress from the north, the west, the south, and the east. I should point out, when I'm using northwest, south, and east, I'm using them in the modern context. You'll notice here, there's the north arrow there. So you'll notice that what is now the modern-day west coast was in fact facing in a northwards direction during the Proterozoic and also in the Cambrian as well. So please bear that in mind. So anyway, in the middle Cambrian, we have the sea begins to transgress from the west, the south, the east, and the north. And so as we move into the late Cambrian, we can see that we have essentially a very extensive body of water. So we have our transcontinental arch here. We have nearly the central and eastern portions of the states are underwater. The western states are underwater. A significant proportion of Canada is also underwater. And by the early Ordovician, you can see we have a body of water, an epiric sea, a shallow epiric sea, that extends all the way from what is the west coast over here, all the way over to what is the east coast over here. So we have a continuous body of water going from one side of the United States to the other. And what we have is a region marked out here by the slightly more white colour. That's going to be a region that's dominated mostly by sandy sediments. So that's material being eroded off the exposed crust here, being transported by rivers, deposited along the coast here. This slightly darker blue area here, this is the area where we're going to get large-scale carbonate deposition taking place. So what about this transgressive sequence? What kind of evidence do we have that it took place? Well, once again, we're actually going back to the Grand Canyon. I know it's come up a couple of times, but here we are again. So at the Grand Canyon, we have early Cambrian rocks that are exposed and eroded. So here we go. So here are the Cambrian rocks down here. They form the Tonto group. So by the middle Cambrian, we have a marine transgression. We see the deposition of the Tapete sandstone. Okay, the Tapete sandstone is a clean sandstone containing ripple marks and small crossbeds. That's essentially a shallow marine coastal sandstone. We then see over the top of the Tapete sandstone, we have the Bright Angel Shale being deposited, so the water depth is increasing. And then over the top of the Bright Angel Shale, we have the Moiré limestone being deposited, and that represents we're in shallow, clear water. So as we head from the Cambrian, as we head through the Cambrian, we go sandstone, mudstone, limestone. So essentially we are heading into, we got a marine transgressive sequence. The water depth is steadily getting deeper as the ocean gets, well, as more and more as the ocean transgresses further and further across North America, or should I say Laurentia. So there, the Tonto group is part of the Sauk sequence. So of course, if we go back to the diagram here, obviously we are going to be down in this area here. That's where the Tonto group is going to be forming. So as the water depth gets higher and higher and higher, this area is initially dominated by sandy sediments, then it gets covered over by muddy sediments, then eventually it gets covered over by carbonate sediments. So obviously, as I said, it has this sandstone, shale, limestone transgressive sequence that tells us the water depth is increasing. And the sequence itself is time transgressive. So the ages of certain beds, e.g. the Moiré limestone, may not be the same in all locations based on the faunal evidence. So evidence shows that the Moiré limestone was already being deposited on the shelf, that's the original coastline, when the deposition of the Tapete sandstone was still happening on the Craton. So what this means is oh, going the wrong way. If we think about this model here, we had the Moiré limestone being deposited here, but as we come this way, we have the Tapete sandstone being deposited over here in the essentially in the coastal region. Now, what's going to happen over time is this coastal region is then going to get covered over by deeper water. That's going to give us the Bright Angel Shale, and then eventually even deeper water. That's going to give us the deposition of the Moiré limestone. So the most important thing to realize is that at the same time we have the limestone deposition going on over here, and we have the Tapete sandstone deposition going on over here. And so we have a time transgressive sequence. Essentially, we have essentially rocks that are the same age here and here, but those rocks are different. And so what we're going to see is that the Bright Angel Shale, essentially in the early Cambrian, is in California. And by the middle Cambrian, it's in the Grand Canyon region. So essentially, as the sea levels begin to rise, we see these fascies begin to shift inland. So if you follow the same layer of rock along, so let's say if you start off on the west coast in California, well, it's now modern day California, and you head towards the center of the United States, and you follow the same layer of rock, as you head towards the center of the United States, that same layer of rock you're following is going to be getting younger. Okay? So the transgression continued into the early Ordovician, and the sea eventually covered the transcontinental arch and much of the shield. So, by the early Ordovician, you can see that a significant portion of North America is underwater, and especially the United States. The United States is nearly completely underwater at this point. So, between the early Ordovician and the middle Ordovician, we see a marine regression taking place. There's a very rapid retreat, which then leaves Laurentia exposed. Now, this exposure doesn't last very long. Okay. Now, remember though, once Laurentia is exposed, obviously erosion takes place, and erosion means lost rock, which means lost time. So essentially, we have an unconformity forming. Now, what we begin to see then is we see the sea regress in the early Ordovician. And then we see a very, very quick turnaround, and we then see the start of the Tippecanoe sequence. So the period of erosion in the early Ordovician was followed by another marine transgression, and that started in the middle Ordovician, and it continued all the way through to the lower Ordovician. Lower Devonian. So the weathering of the quartz-rich sandstones deposited in the Sauk sequence produced an ultra quartz-dominated sandstones, which were deposited as part of what's referred to as the St. Peter sandstone at the base of the Tippecanoe sequence. So the exposure of the sediments deposited essentially in these regions, especially these very, very clean sandstones deposited in these coastal regions, well, when they become exposed to the atmosphere, when the sea regresses, they are eroded and they are further transported, which means that they lose even more of the very, very small portion of feldspar, for instance, is in them. And by the time we make it into the Tippecanoe sequence, these sandstones that are right at the base of the Tippecanoe sequence are ultra pure sandstones, and so they're very, very important when it comes to glass making. So the basal sandstones were followed by widespread carbonate deposition, and this reflects the covering of a substantial portion of Laurentia by shallow warm seas. So, right, what's happening in the case of the Tippecanoe sequence? Well, the Tippecanoe sequence differs slightly from the Sauk. Why? Well, it differs because an even larger portion of Laurentia finds itself underwater. Now, if your continental crust is underwater, it cannot be eroded. If it's not being eroded, you're not producing detrital sediment. If you're not producing detrital sediment, then when that sediment gets deposited into the oceans, only a relatively small portion of it is being, well, only a very small amount is being deposited in the oceans, and so it doesn't really affect the water quality that much. And so what that means is you, during the Tippecanoe sequence, you have a shallow, warm Empiric sea, which is essentially sitting right on the equator, and it has very little detrital sediment being deposited into it, which means the water quality is spectacular. So think of the clear blue seas of the Caribbean here. And that means that what you're going to get is you are going to get massive, absolutely massive carbonate deposition. So essentially the entirety of North America becomes one massive carbonate shelf, with huge quantities of carbonate being formed and deposited. So during the lithification of these carbonates, a lot of them got transformed into dolostone. So if you remember, during the lithification process, if a magnesium-bearing fluid moves through the carbonate that's being lithified, the calcite will alter to give dolomite. And we also at this point have an important event taking place. Along the eastern seaboard, we have the formation of the Tectonic highlands. And this is the result of the destruction of the Iapetus Ocean and the movement of Baltica and Avalonia towards the east coast, or what is now the modern-day east coast of North America. Now, the sequence associated with the Tectonic highlands is dominated by sandstones and shales, which eventually grade into carbonates. That's because obviously you have an area of high ground forming. That area of high ground is exposed to the atmosphere, and so it can be eroded, producing detrital sediment. And so the area around the Tectonic highlands is going to be dominated by clastic sediment, but as soon as you move away from that area, you're going to be heading back onto the carbonate shelf. So okay, so this is our situation. So by the middle Ordovician, you can quite clearly see that we're pretty much back to the kind of situation we had during the Sauk. So you'll notice that a very significant portion of North America is underwater, nearly the entirety of the United States, and a very large portion of Canada. By the time we're into the late Ordovician, we can see that nearly all of the United States is underwater, and even more of Canada is now underwater. This means that there is very little detrital sediment actually being produced. So this water here, this water quality in this region here is going to be spectacular. Okay, and that's going to be great for carbonate formation. You'll also notice if you look towards the top right of the image, you will see the impending collision. Here comes Baltica and here comes Avalonia down here. The collision is on the way. You can see as we move into late Ordovician, they're getting steadily closer, and you can see the crust here is beginning to deform in response to the impending deformation. You can see the formation of what would be the Caledonian highlands up here, and Tectonic highlands starting to form down here. By the early Silurian, we have a regression going on, so a lot of the water retreats off the continent. You'll notice by this point Baltica is now nearly in contact with North America, so here we have the Caledonian highlands here, the Tectonic highlands down here. And by the late Silurian, we can see that Baltica has crashed completely into Laurentia, producing the Caledonian highlands here, and obviously we have the Tectonic highlands forming down here. And by the early Devonian, we have a full marine regression going on, and once again North America, or should I say Laurentia, is now exposed, and massive erosion starts to take place, forming a continent-wide unconformity. So let's just take a second just to make sure we know the conditions required for optimal reef development. So if you want to form a reef, you really need to meet 5 criteria. The first situation is you typically need to be 30 degrees north or south of the equator. Okay, that means you're going to have water that's going to be of sufficient warmth to allow, large-scale coral formation. And coral formation is important because coral reefs form carbonate barriers, and carbonate barriers protect the carbonate shelf, especially carbonate lagoons that form behind them. You also need clear water, you need warm water, and you need shallow water. So that's water depths between 0 and 200 meters. And of course, you need the salinity to be normal. So the shape of the reef that forms will obviously be a reflection of the seafloor topography, and then obviously it'll be also affected by wind direction, and wind direction obviously leads to waves. So the reef will also be shaped by wave action. And most reefs that tend to form are what we refer to as barrier reefs. They are linear bodies, and these barrier reefs will separate a lagoon, a carbonate lagoon behind the reef, from the deeper ocean in front of the reef. So the reef is all important in protecting the carbonate shelf behind it, and that's why reef formation is key to the large-scale formation of carbonates. So you can kind of see it here in this diagram here. So here's our linear reef, okay, and you can see our linear reef is forming a natural barrier. So here we've got the open sea on this side, and the open sea is going to be pushing waves towards the reef, but the reef is going to act as a barrier, and it's going to help to protect the carbonate lagoon behind it. And so it's in the carbonate lagoon where we're going to get large quantities of carbonate forming. Now the reef itself is relatively porous, and it presents a mound-like lithology with a steeply orientated face facing deeper water. And that's steeply orientated because, of course, that's the side that's being hit by wave action, so that side is constantly being eroded, and loose material is falling off this seaward face, and it collects at the bottom, forming what we refer to as the talus. So the talus forms essentially in the forereef, which is the area directly in front of the reef. Okay, so that's why reef formation is all important, because we want to have these carbonate lagoons, because that's where we're going to form large quantities of limestones. And a lot of the limestones that form are dominated by micrite. If you remember, micrite stands for microcrystalline calcite, so it's very, very fine-grained calcite. We're also going to get abundant microorganisms, so we're going to get lots of photosynthesizing blue-green algae in here, and we're also going to get lots of ooid formation in here as well. And obviously, if sufficient restriction occurs, this lagoon can evaporate away, producing layers of evaporites mixed in with the carbonates. So reef formation in the Cambrian was dominated by one type of organism. That's the archaeophytes, which I probably pronounced massively incorrectly. And they are conical shaped organisms. They had perforated walls, and they had shells made of calcium carbonate. You can kind of see them here. That's a general sketch of one. Here's a fossil, and you can kind of see this is a model showing you how they would have grown. Now, the archaeophytes didn't actually make it out of the Cambrian. So by the time we make it into the Ordovician, the archaeophytes are gone, and they're replaced by the stromatoporoids, or should I say stromatoporoids. And they are sponge-like accumulations formed by colonies of photosynthetic organisms. So essentially just kind of imagine a giant stromatolite almost, a giant linear stromatolite or giant mounds of stromatolites forming the barrier here, forming the reef. And so you can see, this is a diagram of them. You can see they'd form layer after layer after layer. They have this very distinctive lumpy appearance on the top. You can kind of see it on the fossil here, how it looks rather lumpy on the top there. And you can see the layering underneath. And this kind of shows you here a section through one of these stromatoporoid reefs. You can see that it consists of lots of broken up pieces of stromatoporoids, okay, mixed in with lots of these nicely layered stromatoporoids. So this area here, this diagram here, probably represents more of this kind of forereef environment where bits are falling off the reef. Now, in the case of the archaeophytes, the reefs that were forming were linear. They were long, they were long linear, continuous bodies. In the case of the stromatoporoids, they would have been arguably what we refer to as patch or mound reefs. So it wouldn't have been a linear body, it would have been lots and lots of mounds, essentially, all in the same kind of area, acting as a barrier. if you get enough mounds close enough to each other, they will obviously form a linear barrier, well, a linear-like barrier that will offer protection to the lagoon from the open ocean. So the stratigraphids reefs persisted throughout the Phanerozoic, so they make their appearance in the Ordovician. They continue all the way through the Phanerozoic, and we get a burst of reef formation occurring between the late Ordovician and through to the Devonian, and that's probably in response to the formation of these nice shallow seas as part of the Tippecanoe marine transgression. And obviously, because Tippecanoe marine transgression covers over such large quantities of Laurentia, it obviously causes the amount of detrital sediment being deposited into the oceans to drop off significantly, producing very, very good water quality, which is great for reef formation. So the Middle Silurian, we have the Great Lakes region is a really good example of what's going on. So during the Silurian, the Michigan Basin developed, producing a circular depression on what was otherwise a relatively shallow Epeiric carbonate-dominated sea. So here we go. So this is the situation. So here we have the Tippecanoe transgression. Most of North America, Laurentia, is underwater. The sea is relatively shallow, relatively detrital sediment free, and so we have the formation of a very, very large carbonate shelf, producing huge quantities of carbonate. Now, on this carbonate shelf, we have the formation of a depression on the sea floor, and that depression begins to fill with sediments. Now, along the margins of this depression, we get the formation of lots and lots of reefs. And so the reefs build up along the margin of the basin that's forming, the Michigan Basin, and eventually those reefs start to link up, and those reefs slowly link up, and they form a continuous circle around the margin of the Michigan Basin, essentially isolating it from the rest of the Epeiric Sea. And that's going to become very, very important because it's going to restrict the inflow of seawater into this basin. So the basin is also known for its pinnacle reefs. So these are very, very small reefs that occur within the basin itself. And if you remember from the previous video, these basins that form, they are not sorry, it wasn't the previous video, it was the video before. They are not produced by tectonic shifts in the kind of plate tectonic fashion. They are produced by subsidence. So faults on the seafloor begin to move, creating a depression. That depression fills with sediment. The weight of that depression pushes the fault blocks down even further, making the basin even deeper. So it fills up with more sediment. That weighs even more, pushing the fault blocks down even further. So the basin gets deeper, and so on. And so this meant, as the Michigan Basin started to fill up with more and more sediment, the floor of the basin started to get pushed further down and down and down. So this means that the reefs within the basin, well, the reefs obviously need to keep themselves typically, within about minimum 200 meters of the surface of the sea. So this meant that as the seafloor subsided, the reefs had to grow upwards in order to stay within this 200 meter limit. And so what happens is the reefs within the Michigan Basin form these very, very large columns, which we refer to as pinnacle reefs, because the reefs themselves are just growing upwards very, very quickly, and so they form this very, very distinct columnar form, and some of them can reach up to 100 meters in height. And so that's showing you that the basin is subsiding. That's a good indicator that the floor of the Michigan Basin is dropping down. Now, in terms of the basin itself, it filled with carbonates, but it also filled with detrital material coming off the Tectonic highlands. So the Tectonic highlands is right here, producing lots and lots of clastic material, and some of that made its way into the Michigan Basin as well. So here we go. So this is our situation. So this is the late Silurian. We have Tectonic highlands here. We have the Caledonian highlands up here, where Baltica's hitting Laurentia. We have the Appalachian Basin here, directly behind the Tectonic highlands, and we have the Michigan Basin right here. And so we have sediment coming off the Tectonic highlands, coming across and entering into the Michigan Basin. But you can see the Michigan Basin itself is isolated, and it's being cut off by a ring of reefs that form along the margin of the basin. So the sea begins to regress in the late Silurian, with evaporite precipitation beginning in the Michigan, Ohio, and Appalachian basins. So as the sea begins to regress, essentially the basin itself begins to become cut off. And so this means that as the basin begins to become cut off, you all of a sudden begin to end up with an isolated body of water in a hot environment, and so you begin to get the formation of evaporites. And the evaporites in the Michigan Basin form a layer that's approximately 1,500 meters thick, so 1.5 kilometers, give or take a little bit. So in terms of the actual formation of the evaporite layer, it could have occurred in one of two ways. The first way is simply the barrier reef restricted the influx of fresh water, or should I say fresh seawater, into the basin. That obviously meant that the basin became restricted, the water evaporated away, the water became more saline, excuse me, and eventually that led to the deposition of evaporites, as essentially the water became saturated with respect to minerals like gypsum and salt, or should I say halite. So that's one way that it could have formed. The other way that these evaporite layers could have formed is, once again, same situation. The basin becomes isolated due to the reefs, the water begins to evaporate away, and so that means the water steadily becomes more and more salt rich, for instance. It becomes more and more rich in dissolved minerals as more and more of the water is lost. Now this means that some of the water in the basin is going to become very, very heavy because it has lots and lots of dissolved constituents in it. And so this heavy water is going to naturally sink to the bottom of the basin where it forms a brine. And this brine can then directly precipitate evaporite minerals onto the seafloor. So you have this layer of brine sitting at the bottom of the Michigan Basin, and that will be directly precipitating evaporite minerals onto the seafloor. So that's another way this could have happened. Now, as part of the lab, we are going to watch these videos here together, and we're going to discuss what you can see. If you want to watch them beforehand, that's fine. What you're going to see is you're going to see a group of scientists. They're on the floor of the Gulf of Mexico. They've got a rover, and they're going around looking at the brines that are forming in the Gulf of Mexico. This one here is going to essentially allow you to look at the density difference between the standard seawater and the brine. And this one here is going to show you an area of brine that essentially is producing its own evaporite minerals on the seafloor, despite being several hundred meters under water. So, regardless of how the evaporites actually formed, as the seawater evaporated away, we would get deposits of carbonate initially, followed by gypsum, and then followed by halite. So we're going to get a layer of carbonate, and then a layer of gypsum and layer of gypsum and halite over the top. Then what's going to happen is every once in a while the reef is going to fail, and that's going to allow a sudden influx of fresh seawater into the basin. That's going to stop evaporite precipitation. At that point we're going to go back into carbonate deposition, and then obviously the reef's going to repair itself. The fresh seawater can no longer come in. That's going to mean eventually we're going to get back to the point when we get evaporite precipitation again. The reef's going to fail, new seawater comes in, stops evaporite deposition, so we're back to carbonate deposition, and then eventually the reef's going to repair itself, large scale evaporation again. That's going to lead to the formation of evaporites. And so if we look at the Michigan Basin sequence, we have layers of carbonates followed by evaporite, carbonate, evaporite, carbonate, evaporite, obviously with layers of sandstone and mudstone mixed into the sequence coming from the erosion of the Tectonic highlands. So what happens at the end of the Tippecanoe sequence? Well, by the early Devonian, the sea had regressed to the Craton margin, leaving only a few interconnected basins. So the Craton was weakly deformed during this period, producing domes, arches, and basins. So during this time frame, the Craton is getting very, very weakly deformed, producing very, very large, broad anticlines and synclines. And these anticlines especially were eroded while the Craton was exposed and then covered by fresh sediments deposited during the transgression of the Kaskaskia Sea during the Middle Devonian. Okay, so let's have a moment. Let's take a moment to actually take a break because I have run long. I apologize for that. So let's stop the presentation here. Take a couple of minutes, get up, have a walk around, go and get a glass of water, and please return. Alright, so during the Paleozoic, we begin to see the formation of the Appalachian mobile belt on what is now the modern eastern side of North America. So the Appalachian Mobile Belt began to form during the Middle Ordovician. Now it's not just one event. It actually consists of, arguably three, maybe four separate orogenic events that all combine together to give us the Appalachian Mobile Belt. So, that's another reason why it's referred to as a mobile belt, because it's not one event. It occurs in, several different events occurring in slightly different locations, meaning the belt isn't actually 100% stationary. So the mountain building was part of the broader tectonic regime that sutured the continents together to form Laurasia by the late Devonian and Pangaea by the end of the Paleozoic. So Laurasia forms when we have the collision of Laurentia and Baltica. So Laurentia and Baltica, and to be honest Avalonia, combined together gives us Laurasia. And then that's formed by the late Devonian. And then after that, we then have the collision of Laurasia with Gondwana, and that gives us the supercontinent Pangaea. So in the late Proterozoic to early Ordovician, the eastern margin of Laurentia was passive, and the Iapetus Ocean was opening to the east and to the south. So all the way through to the early Ordovician, along what is now the modern east coast of North America, we had a nice big ocean basin there called the Iapetus Ocean. Not as big as the Atlantic, but still pretty big. So in the middle Ordovician, the Iapetus Ocean began to close. So a subduction zone opens up, and the seafloor of the Iapetus Ocean begins to be destroyed. And so that begins to bring Laurentia and Baltica towards each other. They start moving towards each other as the ocean crust between them begins to become destroyed. So this collision initially is going to lead to the early stages of the formation of the Appalachian Mobile Belt. And so you can see it here. So these orogenies combined are going to end up giving us the Appalachian Mobile Belt. All right, so here's the basic situation in late Ordovician. So here's the Iapetus Ocean, and we have subduction, and subduction is destroying the Iapetus Ocean, and it's bringing Baltica and Avalonia towards Laurentia. And obviously there is going to be a collision. So along here we're going to end up with the Caledonian orogeny, and down here we're going to end up with the Tectonic Highlands. So the Tectonic Highlands is the opening stage, essentially, of the Appalachian Mobile Belt formation. So what's going on? Now this is a rather complicated situation. So you have to remember, down here, down to the southeast, we actually have Gondwana. It's just down here. Okay, and so what's going on here to actually form the Tectonic Highlands? So this rather interesting block diagram drawn by yours truly hopefully will help to summarize what's going on. So here's Laurentia, us, and here's Gondwana down here, and in between we have a rather large body of water, and we have a lot of oceanic crust in between. Now you can see Baltica and Avalonia are heading this way. That's going to produce the Caledonian Highlands up here. So what's going on down here to give us the Tectonic Highlands? Well, what happens is initially we have Laurentia being eroded, sediment being deposited here along what is now the eastern margin, and we have the oceanic crust starts subducting down underneath the oceanic crust of the Iapetus Ocean, and that creates essentially a chain of volcanic islands sitting just off the coast of Laurentia. Now, because the oceanic crust is subducting down underneath here, it pulls Laurentia in this direction, and obviously eventually that leads to the collision of Laurentia with this island arc, and that leads to the formation of the Tectonic Highlands. Now, once this collision takes place, the direction of subduction shifts. So it was initially coming down towards what we would now consider to be, approximately the south. The direction of subduction shifts towards the north, and that of course produces magma that rises up, feeding volcanoes which are part of the Tectonic Highlands. At the same time, towards Gondwana, we have a situation where we have subduction starting just in front of Gondwana, and that's also helping to destroy the oceanic crust that separates Laurentia and Gondwana, and essentially it's leading to the eventual collision, which is going to give us the complete Appalachian Mobile Belt. So it's not an easy one to understand. It's a rather complicated orogeny. Essentially, all you need to understand is subduction produces a volcanic island arc sitting off the coast of Laurentia. Eventually, that subduction causes Laurentia to crash into the island arc, forming the Tectonic highlands. And then the direction of subduction shifts, and then that creates magma that then feeds volcanoes within the Tectonic highlands. At the same time, we also have subduction on the other side of the ocean basin. That's destroying oceanic crust over here by Gondwana. And that's helping to destroy the oceanic crust, meaning that Gondwana is now on a collision course with Laurentia. So the collision between Laurentia and the island arc caused marine detrital sediments and volcanic rocks to be thrust onto the continent. So this grey block here is all the volcanic and detrital sediments that were essentially in the ocean basin between Laurentia and the island arc. They get compressed and they get forced onto Laurentia, producing the Tectonic highlands. So subduction then switched direction to under Laurentia, producing a chain of highland volcanoes from Newfoundland to Georgia. And so then what happens is once we have the initial highlands, we then have subduction shifts. Magma's produced down here. That magma rises up, feeds volcanoes on the surface, so the tectonic orogeny grows even larger as all of these volcanoes start putting volcanic rocks into the highlands as well, helping to make them larger. So the Appalachian Mobile Belt, of which the Tectonic Highlands was the first part, developed in a region that had been a relatively shallow carbonate platform, which stretched from Newfoundland to Alabama. And that was formed by the first Sauk Sea, the first marine transgression. And the shallow marine carbonates contain stromatolites, mud cracks, and shallow marine fossils, and they were then covered in the middle Ordovician by a sequence of marine black shales, graded beds, coarse sandstones, greywackies, and volcanic deposits. So this is important. So what we've got is we have essentially a sequence of shallow marine carbonates that are forming in the early portion of the Paleozoic. So all the way through from the middle Cambrian all the way through to the early Ordovician, that area is covered by a shallow sea, creating lots and lots of carbonates. And then all of a sudden, in the middle Ordovician, that sequence of carbonates starts getting covered over by large quantities of clastic sediments and volcanic deposits. And so that's a very, very clear indicator that all of a sudden we have sediments, we have crust being pushed up above sea level, and that crust is being eroded, producing these sandstones and greywackies. And so that tells us very, very strongly that the Tectonic orogeny must have started in the middle Ordovician. So these detrital sediments represent the first stages of mountain building and the erosion of the elevated ground produced by the Tectonic orogeny. So the deepening of the carbonate basin on the Appalachian Mobile Belt's western margin resulted in a down warping of the crust due to subduction. So, what are you talking about there, Chris? Well, the answer is, the situation is that if I just go back over to this point here, okay, so what's happening is we have subduction now going underneath Laurentia. We have the Tectonic highlands here, and a portion of crust back here behind the Tectonic orogeny starts to essentially undergo warping. So it starts to warp downwards. So essentially you create a depression here on the backside of the Tectonic orogeny, and that's going to become a basin. It's fault controlled, and so sediments are going to be eroded off the Tectonic highlands here, and they're going to enter this basin back here. And obviously, as we've discussed, as more and more sediment comes into the basin, that puts more weight on the basin floor, pushing the basin floor down, creating more room for more sediment to be added, which pushes the basin floor down further, and so on. And so this is what we begin to see forming on this rear side of the Tectonic Mobile Belt. So when we look at these sediments that are forming on what is now what we would classify as the western side of the belt, we see paleocurrent directions, sedimentary structures, and facies patterns, all indicating that material was coming from the east and coming into the basin. So, of course, under modern orientations, this is the east coast, so material's coming off the high ground here and entering into the basin, so you get coming from east to west. So that makes perfect sense. So the timing of the tectonic orogeny is well constrained, as steeply dipping lower to middle Ordovician beds caused by the orogeny are unconformably overlain by horizontal and shallow dipping Silurian beds. So this gives us excellent timing dating information. So we know we have these clastic sediments being deposited in the middle Ordovician. We have the first indications of deformation actually coming in the lower Ordovician. So that means the collision was underway by the lower Ordovician. That starts, very, very early gentle deformation. And then by the middle Ordovician, we have the main event, producing the tectonic highlands. And then by the time we're into the Silurian, the event has finished, because we now return to the deposition of nice, shallow, almost horizontally dipping Silurian age rocks. And so we have a very, very nice set of dating evidence for the timing of the tectonic orogeny. So the orogeny must therefore have begun between the end of the lower Ordovician and the start of the Silurian. That's the range of time in which the tectonic orogeny occurred. And we're lucky because the tectonic orogeny was associated with the formation of volcanic rocks. We can date those volcanic rocks, and the volcanic rocks date essentially the tectonic orogeny between the middle and late Ordovician. So this kind of gives you some idea of what's going on here. So this is our situation. So this covers the formation of essentially the closure of the Iapetus Ocean. So now this diagram isn't 100% correct. So if we look at this diagram up here, what we can see is the Caledonian Highlands are actually forming up here. The Tectonic Highlands are probably more associated with the impact of this island arc. Okay, so this diagram here isn't quite right. This diagram here suggests the Tectonic Highlands is actually being produced by the collision of Laurentia with with Baltica and Avalonia over here. That's not quite correct. But the diagram itself is actually correct. We do have this body of water here that separated essentially Laurentia from this volcanic island arc. Essentially, the oceanic crust in between them was destroyed, and as eventually the two of them ran into each other, producing the Tectonic Highlands. And so the Tectonic Highlands are associated down here. So we had the Caledonian Mountains forming up here. The Tectonic Highlands are more associated with the collision of Laurentia with essentially a smaller island arc forming down here off the east coast. So within this basin that forms along the western side of the Tectonic Highlands, as you remember, the crust is being down warped by all the sediment, that leads to the formation of what we refer to as a clastic wedge. So a clastic wedge essentially is a wedge-shaped package of sediments. And we see the same sediments that would have been deposited on the eastern margin of the highlands. However, the same sediments would have been deposited on the eastern side of the highlands as well. However, they were obviously destroyed by subduction. So we have the clastic wedge forming here on the western side. That's from material being eroded off the highlands and moving into the Appalachian basin here. Now, we would have had the same sediments being deposited here on the eastern side. However, because this area here is an active subduction zone undergoing active deformation, those sediments just get mixed in and mucked around with as part of the subduction process, so we don't really see them that well. So the clastic wedge that forms is referred to as the Queenston Delta. And what we see is, so these are the Tectonic Highlands here. The Queenston Delta essentially forms a sequence of sediments that are the thickest, closest to the highlands, and the layers of sediment get slightly thinner as you move towards the west. So that's why it has this distinctive wedge shape. So mapping of the delta indicates that around 600,000 cubic kilometers of rock were eroded to make it. And such a volume suggests that the Tectonic Highlands were at least 4,000 meters high, which puts them about the same height as the Rocky Mountains. So they were a pretty substantial mountain range. And the tectonic orogeny, of course, as I said, marks the first stage of the mountain building that produced the Appalachian Mobile Belt. And as the Iapetus Ocean closes further, things are only going to get more fun as Gondwana begins to get closer and closer. Okay, so this is where the second presentation, or the first presentation, ends. So the code word for this presentation is unicorn, as in the mythical beast. So that's unicorn. So keep an eye out for the second presentation coming. Right, take care everyone.